Good day and welcome to One-on-One Maths Private Tutors. Today, we look at the very first topic in O-Level and IGCSE Mathematics, the topic of number, types of numbers. Because in maths, we work with numbers. We have to know the types of numbers that are there. So we'll look at the syllabuses. We have O-Level, IGCSE, and ZIMSEC. In IGCSE, we have two types of papers. We have the extended and the core. And people usually choose the core because it is much simpler. Cambridge has only one set of exams for O-Level as well as ZIMSEC. It is pure maths. Cambridge O-Level are looking at syllabus 4024. For ZIMSEC, we are looking at syllabus 4028. For IGCSE, the code is 0580. So these are the syllabuses we must be looking at. Even for other syllabuses like Aqua, if it is the same level, the topics are almost similar. So we will look at the syllabus requirements. This is for O-Level Cambridge syllabus. The topic number. Candidates are required to identify and use natural numbers, integers, prime numbers, square numbers, cube numbers, common factors. That is the next chapter we are going to look at. Today we are just going to look at the types of numbers. We're also going to look at rational and irrational numbers, what they are. So these are the types of numbers we have under the bracket of real numbers. So that's what we are going to look at. This is the requirement for O-Level Cambridge. For IGCSE Cambridge, identify and use natural numbers, integers, prime numbers, square numbers, cube numbers, real numbers. We are going also to look at rational and irrational numbers. Common factors and common multiples, we are going to look at it in the next chapters. So that is the requirement we are going to look at in the IGCSE, whether it is core or extended. This is required. For ZIMSEC, it is given as number types, and you can see it's under Form 1. The others are full topics we are going to look at: factors and multiples, directed numbers, fractions and percentages, order of operations. We'll see them in coming videos. Factors and multiples, squares and square roots, cubes and cube roots. These are next chapters, but we are going to look at irrational numbers. So number types, which we have mentioned: integers, natural, squares, cubes, rational, irrational numbers. We are going to look at them. So now that we have seen what is required of our syllabus, let's get into the work. Number types. Integers are positive and negative whole numbers. What are whole numbers? Whole numbers are numbers without any fraction. Whole numbers are like 2, 3, 5, 1,000, 1,700, minus 30, minus 50. So integers are positive and negative whole numbers. Now to put them in a set, we can say integers. We'll start from very large whole numbers, so we put 3 dots there to mean that we are starting from a very large, we are going way back. Then we can say minus 3, minus 2, minus 1, 0, 1, 2, 3, comma. Then we put dots also. We must have a comma also here to mean that we're coming way back, and there, comma, it goes on and on. Then we can close the bracket. So we can say integers equal to positive and negative whole numbers, including 0. Okay, so that is integers. This is a set of integers. Minus 50, minus 900, minus 1,000,000, minus 1,000,000,000 is part of integers. So we can see that from these 3 dots, which means it's going on and on. But the character is that they are whole numbers. Whole numbers do not have a decimal point like 2,33. This is not a whole number. because it is a fraction, or 2.5. This is not a whole number because it is a fraction. So we are saying whole numbers, numbers that are without fractions or decimals. Those are integers, both positive and negative. The next type of numbers is natural numbers. Natural numbers are integers that can be used for counting. So the definition will be natural are counting numbers or positive integers starting from 1. When we are counting things, we first started counting 1, 2, 3, 4. That's why we say they are counting numbers, and they are positive integers starting from 1. So 0 is not included. So we can say natural numbers, we are starting from 1, 2, 3, and then put our 3 dots to say on and on and on. Remember, the starting point is 1, and they are positive integers, which means they are positive whole numbers, 1, 2, 3, 4, 5, 6, 7, and so forth. 1 million is a natural number. 1,000,001, as long as it doesn't have a fraction or a decimal. Those are natural numbers. So we can see natural numbers are part of integers. So in our sets, we can say integers, natural numbers. So natural numbers are part of integers. Here we can only have positive, here we can have negative, and they go on and on. The set of natural numbers is infinite. It will never end. How many numbers can you count from 1 going up? Integers also. How many numbers can you count going into the negative? How many numbers can you count going into the positive? It's never ending. In maths, we call that infinite. It means it will never end. Now let's move on to rational numbers. A rational number is a number that can be written as a fraction, a over b, where a and b are integers and b is not equal to 0. Rational numbers, these are numbers that can be expressed as a fraction, a over b, where a and b are integers and b is not equal to 0. So that's how we write it. B is not equal to 0. What happens when we divide by 0? Dividing by 0 will give us an error. Let's look at our calculator and try to divide any number by 0. We say 5 divided by 0, math error. So in mathematics, if you get an error, it means your calculation is not possible. We don't know how many zeros are in 5, but we can say 5 divided by 1. It will give us an answer 5. We know there are 5 ones in 5. That is the first rule. If we are dividing, we should never divide by 0 because it is a mathematical error. It is impossible in mathematics to find out how many zeros are in a number. So a and b are integers, so they can be positive or negative because integers are positive and negative whole numbers. So if a number can be expressed as 2 over 3, this is rational. Minus 7 over minus 9, this is rational. Minus 1 million over 45, this is rational. So if you can make a number become a fraction, then it is rational. The numerator must be an integer, positive or negative. The denominator must be an integer, positive or negative. No fractions. The top part is called the numerator. The bottom part is called the denominator. What about if we have a number like 3? This is an integer. This is also a natural number. We can express it as a fraction by saying 3 over 1. 1 is an integer. You can see there, 1 is an integer. So 3 is a rational number. So we can say all integers and natural numbers are rational. Let's look at a number like 0 0.45. This is a decimal number. Can say this is a terminating decimal. What is a terminating decimal? We know the word terminus is where buses or taxis finally come to a stop. Their end destination. It is the end destination of taxis or buses. So a terminating decimal is a decimal that comes to a stop. There is nothing further there. It's 0.45. It comes to an end. This can be expressed as 0.45 over 1. If we say 0.45 over 1, what do we get? We get 0.45. If we multiply this by 100 over 100 with the aim of making this a whole number, we will get 45 over 100. 1 times 100 is 100. 0.45 times 100 is 45. Okay, why multiply by 100 over 100? 100 over 100 is the same as 1. We can see on our calculator 100 over 100 is the same as 1. So anything you multiply by 1 or divide by 1 will always remain the same thing. So we are saying 45 over 100 is the same as 0.45. Can we prove that? So 45 over 100, 0.45. So this and that is exactly the same. So we have transformed this decimal into a fraction where the numerator and the denominator are integers. So this applies to all terminating decimals. So what can we say? Now we can say terminating decimals are rational. Let's go on to what we call recurring decimals. Now, a recurring decimal has a repeating pattern after the decimal comma. Examples are 0.232323 and so on. So it goes on repeating 2323. So in maths, we write it as 0.23. Then we put a bar on top, or we put 0.23 and put 2 dots on top to show that it is recurring. Another example is 138.66666. So how do we write it down in maths if it goes on and on? We write it as 138.6, then we put a dot. Or we can write it as 138.6 and put a bar on top. Another example is 76.5, 7878, and so forth. So the repeating pattern is on 7, 8. This is also a recurring decimal. So we can write it as 76.5, then 7, 8, and put the bar on top of 7, 8. Okay, which is also equal to 76.5, then 7, 8. We put dots there. Another example, 45.91, 278, 278, 278. We see this repeated pattern going on and on. This will be equal to 45.91278. So we put a bar on top, or 45.91278. Then we put dots on the first and the last number in the repeating pattern. So those are what we call recurring decimals. A decimal with a repeating pattern after the decimal comma. So this repeating pattern will go on and on. Common recurring decimals. We have 0.6666 going on and on, which is 0.6 recurring. This is equal to 2/3. So it can be expressed as a fraction, A over B, where the denominator is not equal to 0, then it is rational. How can we prove it? Let's do 2/3, 0.6 recurring, which means 0.6 going on and on. So recurring decimals are rational. 7 over 9 is 0.7 recurring. So 7 over 9 is equal to 0.7 recurring. So we can see that recurring decimals are rational because they can be expressed in the form A over B. And this B is not equal to 0 because we know division by 0 is not allowed in mathematics. It will give us a mathematical error. It's a calculation that cannot be done. So all integers are rational. Integers include also natural numbers. All terminating decimals, 5.81, can be written as 581 over 100. So they are rational. All recurring decimals, for example, 0.6 recurring can be written as 2/3. So they are rational. Now we go to irrational numbers, the opposite of rational numbers. An irrational number is a number that cannot be written as a fraction, such as √2 or pi. So we have numbers that cannot be expressed as a fraction. Irrational numbers cannot be written as a fraction. Examples are pi. So if we go to our calculator and we say shift pi is equal to, so this goes on and on in a random fashion. It does not have a pattern. Numbers are without a pattern. Right. So we call these irrational numbers. Another example is √2, which is, so these numbers are going on and on. It's only that the calculator display is small. That's why we are seeing only up to this one, but it will go on and on forever. Now, square roots of numbers between perfect squares are also irrational. So we can say, if we have 4 and 5, if we square them, 4 squared is 16. 4 times 4 is 16. This is also the same as saying 4 squared. We shall look at it more when we are doing squares of numbers in another video. And 5 times 5 is equal to 25. 5 squared is equal to 5 times 5, which is 25. 4 is the square root. Square root of 16 is 4. Okay? Square root of 16 is equal to 4. Since 4 squared is 16. Square root of 25 is 5. Square root of 25 is 5. These numbers, 25 and 16, we call them perfect squares because they are obtained from squaring integers. So any square root between 16 and 25 is irrational. Between 16 and 25, we have 17, 18, 19, 20, 21, 22, 23, and 24. So all these, √17 is irrational. √18 is irrational. Square root of 19 is irrational. √20 is irrational. √21 is irrational. √22 is irrational. √23 is irrational. √24 is irrational. So those are easy irrational numbers we can find. Square roots of numbers between perfect squares are irrational. Our perfect squares are 1 squared, 2 squared, 3 squared. 1 squared is 1. 1 times 1 is 1. 2 squared is 2 times 2, which is 4. 3 squared is 3 times 3, which is 9. So any square roots between these numbers are irrational. They cannot be expressed as a fraction A over B, where B is not equal to 0. So in our set, we can see natural numbers and integers are rational. So they can be part of the rational set. So here we can add more examples to say 0.25 terminating decimal or 0.6 recurring, the recurring decimal, any other terminating fraction and recurring decimal. And then on the other side, we have irrational. Examples being root 21, root 2, root 30. If it's not a perfect square, its square root is irrational. Root 40, root 101. All these are examples because these numbers are not perfect squares. Pi, also irrational. Irrational numbers give decimals that do not terminate or recur. They don't have a pattern. Real numbers. The set of real numbers is made up of all rational and irrational numbers. Rational and irrational are real. Now, the rule is if the number gives you a result on a calculator, root 56, this is an irrational number, but it's giving us a result, then it's a real number because it is giving us back a real value. 2/3. It's giving us back a real value, then it's a real number. Let's look at examples of unreal numbers. If we divide by 0, then we get an error. 5 divided by 0 will give us an error. So we have another set of numbers which we are not concerned about, which is the non-real numbers. Any number over 0 is unreal. Or square root of a negative number. You know, square root of 16 is 4. What about square root of minus 16? On our calculator, it will give us an error. Square root of minus 16 error. So these are examples of what are called non-real or imaginary numbers. They are not real, they are imaginary. Then division by 0 and square root of a negative number, for example, are imaginary or not real. But we are mostly concerned in our syllabus with real numbers, which are rational or irrational. On the rational side, we have integers, terminating decimals, and recurring decimals. So that is the explanation of our numbers. Let's look at an example. Sort the numbers in the list below into rational and irrational numbers. So this one 0.8625, terminating decimal, therefore it is rational. Root 12, it is the square root of a number that is not a perfect square. So root of 12 is irrational. For pi, since there is a pi is irrational. If you add anything to an irrational number or multiply an irrational number, it remains irrational. 67/19, it has been expressed as a fraction where the numerator and the denominator are integers, and the denominator is not equal to 0. So this is rational. Square root of 64. 64 is a perfect square. Square root of 64 is equal to 8. You know 8 times 8 is equal to 64. Okay, so square root of 64, as we have seen, is 8. 8 can be expressed as a fraction, 8/1. So it is rational because we have a perfect square there. So that is the types of numbers that we have required by all syllabus, whether it is Cambridge, SIMSEC, or IGCSE. Thank you.